This is a lesson about many mechanisms of alkyl halides, including the SN1, the SN2, the E1, and the E2 reactions. So let's go ahead and start and see what kind of questions we have. Okay, in this question, we're asked to go ahead and take this alkyl halide, a chiral alkyl halide, and we're going to react it with sodium methoxide. Okay, and the solvent for this is going to be methanol. Okay. Now, don't be fooled just because methanol is a protic solvent. The important thing here is to note is that there's no acid catalyst here, because sodium methoxide is actually a strong base right there. The only reason why we had to use methanol for this reaction, which will either be nucleophilic substitution SN2, or perhaps it could be an elimination right there. The only reason why we would use that is basically because of the solubility considerations. It's a very ionic compound, and so therefore you have to use this particular solvent. Okay, so let's go ahead and draw the products here, or draw the reactants, because that's the major thing about this lesson. You have to go ahead and react the two reactants that are given here and give a product. Okay, so let's go ahead and draw that. So first we're asked to draw butane, okay, with a methyl at the 2 position, and then we'll have a bromine at the 1 position. Okay, the next thing we'll draw is the other component, the sodium methoxide, and we won't have to draw the solvent in here. So let me go ahead and put sodium methoxide here. Okay, so I'll go ahead and put in sodium, and methoxide is a combination of methyl oxygen. So we'll go ahead and put those two together. There is the carbon, and finally let's put up the oxygen. Okay, we'll put all our hydrogens in. Okay, and then we'll go ahead and use chemistry to actually show that this is an ionic compound. Okay, and then we'll check whether this is actually an R or S chiral center. So in this particular case, this is priority 1, this is priority 2, this is priority 3. Okay, and so we've really drawn the S version. And since that's the only chiral center in this molecule, now if you had more than one chiral center, you couldn't do this, but since it's the only chiral center, we'll go ahead and hit mirror, and that way we'll convert over to the R. Okay, now that we have this, okay, now we have to decide what to do with this reaction. Okay, so the two things we should note is that first, this is a strong base. This is as strong a base as hydroxide, and the other thing that we have to note here is that this is what we would call either, even though it's primary, we call it sterically hindered. The reason why we do that is because at the position, the vicinal position, okay, we don't have a primary carbon, or excuse me, a secondary carbon. We actually have a tertiary carbon here. Okay, and so in this case, okay, we'll vote against doing an SN2 substitution, because to try to do the SN2 substitution, this nucleophile would have to come from the backside here. Okay, and of course we can't do an SN1 or an E1 reaction in this case, because this is a primary carbon, and you can't do E1s or SN1s in these cases right there. Okay, so because of that, the only other choice that we have left to do in this particular reaction is to go ahead and do an E2 elimination. So remember, to do E2 eliminations, what you have to do is you have to make sure that the leaving group, okay, and the vicinal hydrogen, okay, are actually anti to each other. So that's what I've been trying to do here. Let me go ahead and twist this so it's this way. Okay, and then I'll come in with the base. So let me move this over into place. Remember, what we're going to do is we're going to go ahead and use the electrons from the base to pick up the vicinal hydrogen. And in this case, there's no trying to decide whether it's going to be Zaitsev or Hoffman, because there's only actually one hydrogen to remove, only one vicinal hydrogen. Okay, because of that, then we'll go ahead and move here on the side so we can manipulate this more easily. And then we'll go ahead and use chemistry to go ahead and make a bond here. Okay, and then lastly, we'll go ahead and take these electrons here, okay, and use this to push this out. Okay, so in this case, we've done an E2 elimination, and again, we did the E2 elimination for several reasons. Okay, one of them is that this is too sterically hindered to do an SN2 substitution, where the the bromine used to be connected. And the other reason why we did E2 is because, or we ended up doing E2, is because of increased steric hindrance. And we didn't do an E1 or an SN1 because this was a primary alkyl halide, in which case you cannot do those mechanisms because you cannot form the the stable carbocation needed for that reaction. Okay, so that's all we needed in this case, so let's go ahead and continue. Okay, let's see what else we have on here. Okay, now we have a different compound. Okay, so we'll draw a hexane here, and we'll put a methyl at the 3 position, and we'll also put a bromine there. Okay, and we'll go ahead and add our hydrogens, and then we'll hit arrange. Okay, after that we'll go ahead and add sodium iodide. So let's put sodium iodide in here. Okay, so here's sodium, and then we'll put the iodine in over here. Okay, after doing that, we'll go ahead and hit arrange. Okay, and then we'll think about what we have to do in this particular case, right? Okay, so we'll go ahead and ionize off this, or ionize this to, because it's a salt. Remember, iodine is much more electronegative than sodium. Okay, after doing that, then we have to consider what mechanism are we going to do here. Okay, well, first of all, it's a tertiary alkyl halides, so we can't do an SN2 substitution. Okay, next we have to consider, well, is this compound basic? Okay, if it were basic, then we could go ahead and do an E2 elimination, which we can't do here. Okay, so all we have left to do here, even though these are very poor conditions, okay, and the conditions here are to use what? Acetone, which is an aprotic solvent. So this reaction will not occur very quickly right here, but we're going to go ahead and do it. What would it do, but what will it do very slowly? And the answer is, well, okay, eventually this has to ionize off. Okay, and once you do that, okay, then you have to go ahead and substitute, okay, or replace this, okay, replace the iodine for the bromine. Now, what mechanism or what kind of stereochemistry should we come in here? And the answer is, well, okay, on this particular one, it doesn't really matter whether you're going to show it coming from this side or whether you go ahead and attach from the other side, because remember, the intermediate in this case was what? Was a chiral center. Okay. So I'm going to go ahead and show it on this side, which would be retention of configuration, or on the other side it was actually repulsion of configuration. In fact, that's one thing I didn't do, okay? But let me undo here and let's back up here, because remember it said to start off with R, and we didn't really test whether this was R or S. So let's go ahead and do that. Okay, and in this case this is priority 1, this is priority 2, this is priority 3. So we'll go ahead and hit mirror because we actually drew S, and so this is R. Okay, and so once we do that, okay, what I want to do is I'm just going to go ahead and ionize off again the iodine. Okay, and after ionizing off the iodine, okay, then what you can try, okay, if you have to do this lesson more than once, okay, is you can try to see whether this particular question will accept, retention or inversion of configuration. So in this case, I'm going to go ahead and try. Okay, I'm going to try retention of configuration, right? And that would also show that this was not an SN2 substitution. Okay, now the reason why we're doing this reaction in acetone is basically because, okay, sodium bromide is insoluble in acetone, whereas sodium iodide was soluble in acetone. In which case, what's driving this reaction is that you're going from a soluble reactant to an insoluble product right here. So keep everything in the picture right there, and let's go ahead and test if this is actually what the program wanted. Okay? And of course, you could have also tested, you know, by adding on the other side, and for this particular question, it'll accept any enantiomer because remember, in this reaction, when you lose control of your stereochemistry, when you lose your chiral center and you make a carbocation, you can actually make a racemic mixture. But this one will not ask you to draw the enantiomer. Okay, in the next question, we're asked to draw the product of reaction of 2-chloropropane and water. So we'll introduce our chlorine. Okay, and then we'll introduce some water. Okay, so we'll add everything together. Okay, and so we'll move the water over here. Okay, and so what we have here is a secondary alkyl halide, and we have a protic solvent like water. Okay, so what you have to consider now, this is a secondary alkyl halide which can ionize off to make a carbocation, And what you have here is a good product solvent for doing that. And the reason why it's a good product solvent for that is because you can go ahead and do hydrogen bonding. Okay, so let me show some hydrogen bonding here. I take electrons from here, okay, and share them over here. Okay, and with that hydrogen bonding now, I'm going to go ahead and ionize off the chlorine to make a carbocation. Okay, and once I have that carbocation, okay, eventually I'll have some actual water or some extra water in this reaction. So let me go ahead and let me go ahead and actually just use this water that's on the screen here, because that's all we were given, 2-chloropropane and water. And let me go ahead and react it with this. Okay, so to do that, let me go ahead and roll this around. Okay, because the hydrogens aren't the nucleophilic part of water; it's actually the water itself, the oxygen. Okay, so once I rolled it around, okay, then I can go ahead and connect this oxygen over to here. Okay, and then I'll hit arrange. Okay. Now I think in this particular problem, okay, what we should do is just go ahead and leave this the way it is. Okay. Okay. Since we're asked to draw the products, then we're going to leave everything on the screen like it is right there. You may ask, well, why not draw HCl? Okay, and the reason is because, okay, when you do this particular reaction, okay, unless you do the workup, okay, the proton is more likely to be on an oxygen, okay, than it is to be associated with chlorine right there. Okay, so let me leave this proton over here. Okay, and once you do that, okay, just realize that only in the workup would you get rid of the HCl like this. So I think this is what we should draw for this particular reaction. Okay, you should also be keeping track of the messages that you get for these lessons. Okay, remember that if you're getting the message enantiomer of, then you had some problem with the stereochemistry that you were either supposed to do, inversion basically, because you're just doing SN2 substitutions that would lead to a different stereochemistry. Okay, if you get the message diastereomer of, that means that you had more than one chiral center and you didn't really deal with the stereochemistry there, or perhaps you do cis versus trans like this. And if you get the message constitutional isomer, that means that you didn't connect your atoms correctly. And remember, if you get the message non-isomeric, that means you didn't put enough components. Maybe you didn't put the right reactants on the screen right there, and so that's why you're not going to have the right number of atoms to answer these questions. Okay, in the next question, we're asked to react iodomethane and sodium methoxide. Okay, so there'll be 2 carbons in this, and again, the solvent was just chosen to make the sodium methoxide soluble. Okay, and so let me put my iodine in here. Okay, which will be the alkyl halide, and I'll put sodium methoxide in here, so I need oxygen. Okay, so here's our oxygen. Let me add the electrons. Okay, and then I'll go ahead and convert the hydrogen over to a sodium. Okay, and then I'll use chemistry to go ahead and show that this is actually an ionic compound, and that's why I needed the methanol as a solvent for this. Okay, so in this case, okay, we have a methyl halide, and we have a very strong base. Okay, but we don't have to worry about eliminations. Okay, for 2 reasons. One of them is that there's no steric hindrance, but the more important reason is that there is no vicinal carbon and vicinal hydrogen that you would have to deal with elimination reactions. Okay, because of that, all I have to do then is go ahead and do an SN2 substitution. Okay, and we hit arrange. Okay, and remember that sodium is a spectator, right? So it's not going to really bond to anything. And so all I need to draw on the screen right here is basically methyl ether. And this reaction that we just reacted, an alkoxide, the sodium methoxide itself right here, reacting with an alkyl halide to make an ether. This actually is called the Williamson ether synthesis right there. So if you look in your text, you can actually find this reaction labeled as such. Okay, in the next lesson, we're going to draw the major products of R2-iodobutane and potassium cyanide. Okay, so we'll put our butane in here. Okay, and we'll put our iodine in the second position. Okay, and we'll go ahead and also draw our potassium cyanide. So we have to go back to carbon. Okay, and you should know that cyanide is actually a carbon nitrogen triple bond compound. Okay, and so that should be nitrogen, not to confuse with sodium. This is just an N, not an Na. And I'll go ahead and add the hydrogens. I'll hit arrange, and I'll convert this hydrogen over to a potassium. Okay, and once I do that, then I realize that carbon is a lot more electronegative than potassium, so this is really an ionic compound. And then I'll just check the stereochemistry of the alkyl halide. So this is priority 1, 2, 3. Okay, and I'll hit arrange. Okay, and so what I have here is I have a secondary alkyl halide, and I have sodium cyanide, which is a very good nucleophile. Okay, because it's a carbon nucleophile. Now you're going to react with this carbon, and you're not going to react with the sodium itself right here. Okay, and then the next thing you'll notice is that yes, this is a protic solvent, and it would promote SN1 type reactions right here. But just keep in mind that you have a good nucleophile, and the reason why we had to use this solvent was again for solubility reasons right here. Okay, and so we have our good nucleophile. So let's just go ahead and do an SN2 substitution. Okay. Again, why are we not doing SN1? And the reason is because we don't really have an acid catalyst to promote this leaving here. Okay, and the other reason too is that rather than just having a poor nucleophile like ethanol, okay, we have a good nucleophile like potassium cyanide. So let's go ahead and do our SN2 substitution, right? And we'll do this, and we'll substitute, and we'll hit arrange. Okay, and so what we should get to is inversion and configuration. So whether when we started off with R, now if you check the stereochemistry, the stereochemistry should now be 1, 2, 3. Okay, so now we've got an inversion, so then this will be the S configuration now. Okay, let's try another question. Okay. Here we have 1-chloro-4-methyl-hexane, and we have potassium tert-butoxide, and this is a fancy way of saying tert-butyl alcohol. Okay, and again, we're using this solvent because of solubility reasons for the potassium tert-butoxide. The other thing too is that actually this potassium tert-butoxide can be generated by actually taking this alcohol and dropping potassium metal in it. Now normally you would do this under inert conditions so that any large evolution of hydrogen gas doesn't actually catch on fire, because potassium is a very dangerous metal. It's a very pyrophoric metal. It catches with moisture. It actually generates hydrogen gas very quickly because it's a very electronegative atom, and therefore you would get an explosion or a fire occurring. Okay, but if you don't do it in the presence of oxygen, then you can go ahead and safely add it to this compound and make this strong base. Okay, so that was our hint right there. This is a strong base. It's a big base also. That's another thing we should realize. So in this case, we'll go ahead and put a methyl at the 4th position. And the next thing we'll do is we'll go ahead and add a chlorine, okay, at the 1st position. Okay, we'll check the stereochemistry of the product after we've added hydrogens. So in this case, this is actually the S configuration. So we'll hit mirror, and now it's the R configuration. Okay, and the next thing we'll do is we'll go ahead and put our big base in there, the potassium tert-butoxide. Okay, so we'll need 4 carbons there. Okay, and we'll add our oxygen. Okay, we'll add our hydrogens. Okay, and we'll convert this hydrogen over to a potassium. Okay, and once we do that, we should realize that actually this is an ionic compound. Okay, and I'll just go ahead and roll this around, okay, because I want my electrophilic carbon to react with my nucleophilic reagent. Okay, but what we have here, okay, even though this is a primary alkyl halide, okay, what we have is a very big sterically hindered base right here. So what we're going to have to do then is we're going to have to go ahead and do an E2 elimination, okay, rather than doing an SN2 substitution. Okay, so what I'm going to do then is I'm going to go ahead and move things or twist things around, okay, so that I can have one hydrogen actually anti to the leaving group, to the chlorine in this case. So let me go ahead and do that. Okay. And let me go ahead and use this big base. Okay, let me fit this on the screen here. Okay, let me try to use, even with such small characters here. Well, let me resize it so I can see everything here, okay? At least I need to be able to see these components. So let's go ahead and use chemistry. Okay, so we'll move the electrons from here, okay, to pick up the hydrogen from there, right? And then we'll take the electrons here, and we'll use them to kick out the chlorine. Okay, and when we do that, okay, then we'll go ahead and see all the components on the screen. And so now I've generated some more tert-butyl alcohol, or tertiary butyl alcohol, which is that 2-methylpropane 2-ol. Okay, and my byproducts in this particular screen, okay, will be what? Okay, potassium chloride, and my major organic product in this particular case, okay, is actually an alkene. Okay, and again, this happened because this is a big base, and this is a primary alkyl halide. Okay. Okay, now I go back to iodomethane, a small, not sterically hindered, and besides it doesn't have any vicinal hydrogens, and I have my big base again. Okay. So in this case, okay, we called it something else. We call it sodium tert-butoxide. Okay, and rather than calling it by the 2-methyl propane 2-ol name, we call it just tert-butyl alcohol in this case. But this is just the solvent right there. Okay, so I'm going to back up here, okay, and bring back this picture. In fact, I'm going to back up a few steps right here because I want to go back to my potassium tert-butoxide, which is the base that we have here. Okay, so here's the potassium there. Okay, and then what I need to do, okay, is I'm going to go ahead and delete everything else from here, or most everything else that's on here. Okay, so let me go ahead and delete all these hydrogens here. Okay, this is just supposedly so that I can go ahead and save some time drying all these reagents right here. Okay, after a while you might realize that you maybe should have clicked clear and not gone back and erased everything. Okay, but let me go ahead and do it anyway, since I'm so close. Let me convert over that chlorine over to an iodide. Okay, let me add all my hydrogens. Okay, now be very careful. What I just did right now, okay, was something bad right here, because see, I had a potassium. That's actually a potassium right there, and that particular potassium, right, was by itself right there, and so that's why it actually got hydrogen added to it. So I'm going to go back now. I'm going to delete that extra hydrogen there. Okay, let me hit arrange here, or let me at least fit everything onto the screen right here. Okay, so in this case, what we're going to do, we're going to do an SN2 substitution, and again, it's because we can't do an E2 elimination here, because even though this is a big base, you know, there's no vicinal hydrogen to remove from here. So let me go ahead and just do my SN2 substitution. Remember, these are not the conditions to promote an SN1 or to have an SN1 substitution, especially because it's a primary, excuse me, it's even less than a primary carbon, it's a methyl carbon. Okay, so we couldn't make a carbocation there. Again, this is a Williamson ether synthesis because you're taking an alkyl halide with an alkoxide, something with an O- in it, and you're making actually a methyl T-butyl alcohol. Okay, and this particular compound is interesting because this ether, okay, is actually, or was used before people started using ethanol and gasoline. They actually used to use this ether, okay, as the oxygen source in gasoline. Okay, and that's important to know because even though you go to a fuel pump and it says oxygenated fuel, by no means should you mix up gasoline and oxygen together. Okay, that's not what they mean. They really mean that you add some compound in there, an alcohol, or in this case an ether. You add it in there like this so that when you actually do internal combustion in your engine, there's already a source of oxygen that will help everything to burn more cleanly or to burn more completely to make carbon dioxide, as opposed to other components like carbon monoxide, which is not fully oxidized. Okay, so let's see what we did wrong in this particular case. And I hope you see that what I did wrong is that in this case we were supposed to be using sodium tert-butoxide, and what I used in this case was actually potassium tert-butoxide. So that's why I got the message that I got, non-isomeric. okay, but in reality the mechanism and the answer would be correct. So please don't repeat the mistake I just made. Okay, here's another question, okay, and this is a very interesting question, so let's go ahead and draw the whole thing out. So I have cyclohexane, okay, and I'm going to have a methyl in here, and I'm going to have an iodine in here. Okay, so I have my iodine at the 1 position and the methyl at the 2 position, just because the smallest numbering scheme is 1, 2, no matter which way, but I comes before M. Okay, and then I'm going to go ahead and put potassium methoxide in here. So let me move this. Okay, and this time we won't make a mistake of which spectre element to have. So let's put our methoxide in here. And oxygen, because it's an alkoxide. That's why it's called an oxide also. And then let me add the hydrogens. And then finally I'll go ahead and put potassium in here. Okay. Okay, once we do that now, let's go ahead and roll this around. Okay, and let's check whether this is actually the RR component. Okay, and so, well, let me also ionize off or separate the potassium and the oxygen here, remembering that this is an ionic compound, a salt. Okay, so let's check this. Okay, so this is priority 1, this is priority 2, this is priority 3, so this is R on this chiral center right here. On this carbon right here, this is priority 1, this is priority 2, this is 3. So this is actually S. So what we need to do then is, let me go ahead and roll the molecule on the side right here. And I need to change the chiral center here. So because making the mirror image of this would actually convert this over from the RS compound to the SR compound. Okay, I'm not going to use mirror, so I actually have to come in here, okay, and change this by changing the position of these two atoms right here. Okay. Okay. Once I do that, okay, then I'll go ahead and convert this also to a chair. Okay. Let me try to convert this ring over here to a chair. Okay. Let me move this a little farther over here. Okay, and then I'm almost ready to go ahead and do my reaction. Okay. So in this particular reaction, okay, we have a strong base. Okay, never mind that it's an ethanol. Okay, but we have a strong base. So we're probably going to do an E2 elimination here. Okay, so whenever you see a strong base, something strong or stronger in terms of basicity, and it doesn't matter whether, well, when you see that, okay, then, and you have any type of steric hindrance right here, you're not going to do an SN2 substitution. You're going to go ahead and do an E2 elimination. Okay, now all we have to decide is to which side. Should we go ahead and eliminate this hydrogen to make this the Zaitsev product? Or should we eliminate from one of these two hydrogens to go ahead and make a Hofmann product? And the answer is, remember that to do an E2 elimination, you need to go ahead and do a concerted, right, anti-elimination. And so in this case, you need to find which group is actually anti to the leaving group or the iodine. So in this case, okay, you can't use this hydrogen and you can't use this hydrogen because they are not anti to the iodine. And even if you were to swing this iodine into the equatorial position right here, that would not solve your problems. So that's why what we're going to do is go ahead and use this base, okay, to actually pick up a hydrogen, okay, or to pick up this axial hydrogen right here. So let me go ahead and do that, okay. This may be far away, but let me pick up the hydrogen here. Okay, take these electrons now and use them to make a double bond here, okay, and kick out iodine. Okay, and when I do that, okay, then I'll get to my product. Okay, so let me move this molecule out of the way and this one out of the way, and also this one out of the way so you can see everything, and let me hit arrange. Okay, and that's why in this particular case, the kind of product that we made, okay, was what? Okay, we didn't do anything to the chiral center, at least at the chiral center at the carbon, right? So this should still be R, okay, configuration. And then over here, the double bond was created to make a Hofmann product, not a Zaitsev product. Okay? Otherwise, if this had been an acyclic compound, you should actually draw the Zaitsev product because you would have been able to rotate along this bond so that one of these, so that this particular hydrogen, right, the poorer, the carbon that has the least hydrogen on it would be the one that you would deprotonate. Okay, but since this is a cyclic example, right, and the iodine has to be anti, that's why we had to draw the Hoffman product. Okay, so now we have bromoethane. So that's 2 carbons on each side, both for the bromoethane and the ethanol. Okay, and let me go ahead and put the bromine in here. Okay, and then let's go ahead and make the alcohol. Okay, put everything in here, right here. Okay, so what we have here now is a primary alkyl halide, and what we have here is a protic solvent. We're not given a good nucleophile. Okay, so these are not the conditions conducive to do anything in reality. So let's go through here and see why in this particular case we cannot do an SN1 or an SN2 or an E1 or an E2. Okay, so let's propose that we want to do an SN1. Okay, to do an SN1, we do have the favorable solvent, which is the protic solvent. Okay, but we don't have the favorable alkyl halide, because remember, for an SN1 you need to have either a secondary or a tertiary alkyl halide, right? SN1 works best with what? With a tertiary alkyl halide. Okay, so that's why we cannot do an SN1 substitution here. And so since we can't form a carbocation here or ionize off this bromine, then we can't do an E1 elimination either. Okay. Okay, and so all we have left, right, is to go ahead and try. Well, let's try an SN2. What would you need to do an SN2 reaction? Well, you would need a good nucleophile. And oxygen is not a good nucleophile, because remember, good nucleophiles on the second row of the periodic table, okay, are those that are on the left side or go towards the left, right? And poor nucleophiles are towards the right, and so that would be oxygen. Okay? And then finally, we know that we're not going to do an E2 elimination because we don't have the basic conditions that are necessary to go ahead and deprotonate this carbon right here to go ahead and cause the formation of a double bond. So in this case, all you have to do is draw the components, and if you want to tell the program that you want nothing to occur, then go ahead and just press continue. Okay, now we have our last question for this cycle. There's actually 20 questions to choose from this lesson, and if you don't hurry up to do this sooner, I might actually add some more. Okay, so let me go ahead and draw the reactant again. So here we have butane. Okay, and we have 1 chloro. Well, there's going to be a methyl here. Okay, and let's go ahead and see this, and let's put the chlorine here. Okay, and then let's draw the methanol again. Okay, so let's put methanol here. Okay, and here's the oxygen. Let's put oxygen to make methanol here. Let's put everything together, hit arrange. Okay, and so once we do that, let's look at the configuration. Is this R or S? And so this is priority 1, priority 2. So this is actually the S configuration. So let me go ahead and hit mirror. Okay, this is the R configuration. So in this particular example, this is just like the previous question. This is a primary carbon. Okay, and primary carbons, even though you have a protic solvent, it's not conducive to actually ionize off the chlorine, okay, by hydrogen bonding, right? Because you cannot make primary carbocations. So if you cannot make primary carbocations, you cannot do the SN1, you cannot do the E1 elimination. And again, this solvent is not basic, so I can't do E2, right? And it's not a good nucleophile, so I cannot do an SN2 reaction. So again, for this question, I should just go ahead and leave everything like it is. Okay? So anyway, in this lesson, you'll be given a choice of either methyl, primary hindered, secondary, or tertiary alkyl halides. You'll be given a choice to actually react with just a solvent, okay, which are poor nucleophiles, a protic solvent, okay, which are conducive to SN1 type reactions. You'll be given also the choice of reacting with good nucleophiles, which are conducive for doing SN2 substitutions. Or you might be given a strong base, right? Something as strong a base as hydroxide. Or you may be given a strong base, which is also big. Okay, those will be all the choices you have, and that's why, if you think of all the combinations, there's 5 combinations of alkyl halides to choose from, and there's 4 types of reagents that you might be given to react with, and so that's why I say there's about 20 questions in here, and you should be able to go ahead and complete this lesson.